Hi, everyone, and welcome back to Organic Chemistry on YouTube. Today, we're going to talk about the oxidation of alkynes to carboxylic acid using the oxidative cleavage method known as ozonolysis. So this reaction is actually quite similar to the alkene ozonolysis reaction in the sense that we're adding ozone, O3, to an alkene. This reaction is more mechanistically complex, and we'll cover some parts of it in this episode. And this affords ultimately two equivalents of carboxylic acids. So let's get into the mechanism. It's in the presence of ozone, cold temperatures, followed by water. You're going to get these two products. And they're different products because the R group on either side of the alkyne is different. So the first step is a 1,3-dipolar cycloaddition of ozone to the alkyne. So three arrows all moving at the same time. So this is a concerted reaction and would end up being a stereospecific reaction. In the case of the alkene, the product is known as a primary ozonide. And it looks like this. Now, in this case, instead of the alkene, in this case, as opposed to the alkene reaction, we now have a double bond at the bottom of this molecule that I've bolded. This also means that this ozonide stays intact and doesn't break apart into two different species. The two lone pairs, which I'm bolding here, come down to form a carbon-oxygen double bond on the right side of the molecule. The carbon-carbon pi bond moves on to make a carbon-oxygen double bond. And at the top, this oxygen-oxygen single bond breaks to form an O-. Now let's show those products. So what you'll notice here is we have on one side of the molecule a ketone, and on the other side, a carbonyl oxide. The mechanism to get to the carboxylic acids is actually quite complicated, but basically just requires water. At some point during these steps, you'll have an anhydride form. And that will lead to the two carboxylic acid products. This anhydride intermediate will become extremely important later in organic chemistry too. But for now, I just want to point it out as a key intermediate from the alkyne to the carboxylic acids. Some questions you might want to ask in office hour. One, well, can you write out the full mechanism with all the rearrangements that we can't do in 5 minutes or less? In this reaction with the alkyne, why isn't dimethyl sulfide required? And three, can I use potassium permanganate instead of ozonolysis as a way to get to the carboxylic acids? With that, that's been Organic Chemistry in 5 minutes or less. Thanks for tuning in.